A water trough is 10 meters long and a cross section has the shape of an isosceles trapezoid that is 30 centimeters wide at the bottom, 80 centimeters wide at the top, and has a height of 50 centimeters. If the trough is being filled with water at a rate of 0.2 meters cubic meters per minute, how fast is the water level rising when the water is 30 centimeters deep? So what we see here, let's think about what are the derivatives we need to find. Okay, so we're given some information about this derivative. How do I know it's a derivative? It's because notice, I mean, by the units here, I'm measuring volume per minute, volume per time. We could think of it that way. And so this information, if I just pull that out for a moment, I have this information about the change of volume with respect to time. This is a constant 0.2 cubic meters per minute, where I'm measuring distance in meters and I'm measuring minutes, time in minutes, excuse me. The other thing then we can see are words like fast and rising. These are words that describe a rate of change. The rate of change of what? Of the water level. If we call the water level, for example, just H right here, how deep is the water at any given time, then we are trying to figure out what is the change of height with respect to time at the moment that the height is equal to 30 centimeters, for which we see right here. This is the unknown that we're trying to find. So we have a known derivative with respect to volume, and we have an unknown derivative with respect to the height right there. And so we have to find a connection that we have to find a relationship that connects the volume and the height together. And so when we think of this water trough right here, what we're thinking of, it's kind of like something, it would look kind of like a really long rain gutter or something like that. We see this kind of picture right here. And so we're trying to find the volume of this thing right here, for which then the height would be in connection right there. So yeah, it seems like the volume formula might be the right way to approach this thing. So I want to mention that in general, if you have some type of prism, it doesn't matter how complicated the face is. If you stretch this face in the third dimension, right, the volume of the prism is just going to equal the area of a single face times the length of that said prism, right? So area times length. That gives you the volume of a prism. Now, that doesn't matter if you have a cylinder, which of course is just a circular prism, rectangular prism, triangular prism, or in this case, this water trough is a trapezoidal prism. We need to take the area of the face. Our face, of course, is going to be this trapezoid right here, times it by the length. Now, the length we already know, that's going to be 10. So we need to times that by the area. And so notice how the length of this water trough, that's that length of the prism, that's going to be 10 meters long. So let's try to figure out the cross-sectional area a little bit better before going on. One other thing I should mention here is that you'll notice that the volume, the derivative there was being measured in meters cubed per minute. We also have the length in 10 meters. We have these other measurements in centimeters right here, right? We have this mismatch of lengths. We need to convert everything to the same length to avoid some potential calculational errors that could creep up later on. The easiest way to do that is to actually convert all of the centimeters into meters. So instead of 80 centimeters, we're going to get 0.8 meters. Instead of 30 centimeters, we're going to get 0.3 meters. And instead of 50 centimeters, we're going to get 0.5 meters, like so. You can also see this diagram. I've shown you what a cross section is going to look like, where we have a typical water level at some moment of time, right, going on right here. If we want to find the area of this trapezoid, so we need to find the area of just not the whole thing, but we need the area of just the water, where the water is going to be. That would give us then the volume, because we're inserting volume over time. Okay, so how do you find the volume of trapezoid? Well, it's significant that it's an isosceles trapezoid. What does that mean? Well, kind of like an isosceles triangle, it means that two of the sides are congruent to each other. And given that it's a trapezoid, the two not necessarily parallel sides, because trapezoids always have at least one pair of parallel lines there. The two not necessarily parallel sides, those are going to be congruent. That's what an isosceles trapezoid means in this situation. And that symmetry is going to be useful for us. Because notice, if you were to snip off this triangle right here, right, you snip it off and you move it over here, then you actually form what turns out to be a rectangle, for which the length of the rectangle is equal to the height of this original trapezoid. And then the width is equal to just the shorter side plus this extra dimension A. So let's investigate what that means a little bit here. And I'm going to write this over here. Then so we get 10 times, well, again, one dimension of that one dimension of that rectangle is going to be h, the height, the original height. But then we have to multiply it by this 0.3 plus the a value. That was the other dimension. So how do we figure out the a value? Well, looking at the diagram right here, I'm going to try to make an argument using similar triangles, where you have this little triangle right here that involves the a on top and the h to the side. So let me copy this over here. So you have h over here and a over here. And then I want to compare that to a triangle which has the same angle measurements, which you're going to see that triangle over here is exactly going to do it. You'll notice that both of these triangles are right triangles, so they both have a 90-degree angle. And then this angle right here is identical to itself, so they're going to be equal. And then the other angles would have to be congruent, as the angle sum will add up to 180 degrees. So therefore, we have similar triangles, and we have this bigger triangle for which this side right here will just be the 0.5 that we see. What about this side on the top? Well, notice that if you look at the entire top of the trapezoid, you have 0.8 going on right here. And then of that 0.8, 0.3 of them are being taken care of right here. If this value called x, the fact that it's an isosceles trapezoid is significant because by symmetry we get x over here. So we're going to get that 2, basically we get that 2x plus 0.3 is equal to 0.8. If you solve for x, you're going to get x is equal to 0.25. So we put that in right here. And therefore, if we compare these two triangles together, these two triangles are proportional to each other, we're going to get that a over h coincides with 0.25 over 0.5, which you can actually simplify that fraction. That just becomes 1/2. Therefore, a is equal to 1/2 h, or I'm actually going to prefer this as 0.5 h, and we're going to plug this in for a right here. Therefore, the volume of this trough turns out to be 10h times 0.3 plus 0.5h. And then just to kind of simplify the arithmetic, I'm going to distribute this 10 through, because multiplying by 10 just moves the decimal place by 1, right? So we get that the volume equals h times 3 plus 5h. I'm also going to distribute the h through, and so we get 3h plus 5h squared. We're now ready to take the derivative of both sides, and we're going to take the derivative with respect to time, d dt, like so. So the derivative of volume, that's just going to be v prime. That's all we need to know about that one. And then on the right-hand side, by the usual rules of derivatives, the derivative is going to look like, taking the derivative with respect to time here, we're going to get 3h prime plus 10h h prime. So when you take the derivative of the 5h squared, the outer derivative is going to be 5 times 2h, giving us the 10h, and then the inner derivative is going to be the h prime. I'm going to factor out the h prime, because h prime is what we're trying to solve in this situation. If you divide both sides by the 3 plus 10h, you then have solved for h prime in that situation. So h prime is equal to v prime over 3 plus 10h. All right, so we aren't after after any old h prime. We're after a specific h prime. We need to find the derivative of h with respect to time when the height, remember, was 30 centimeters. But we need the units to be consistent, so we'll actually do 0.3 meters in this situation. So then, remember the change of volume was 0.2 cubic meters per minute, so we're going to get 0.2 on top. You get 3 plus 10 times the 0.3. And now just try to simplify this thing. You get 0.2 over 3 plus 3. 3 plus 3, of course, is a 6. So we end up with 0.2 over 6. If you want to move the decimal place there, you're going to get 2 over 60, or in other words, 1 over 30. 1 over 30 what? Well, this is going to be measuring, of course, meters per minute. Those are our units right here. For which then, if we approximate that, that would be more useful in this situation. 1/30th becomes 0.033 meters per minute. But as we were originally measuring the height in centimeters, it might make sense to switch back to centimeters per minute. So times this by 100, you get 3.3 centimeters per minute. And so that tells us how quickly the water is rising inside of our water trough at the moment that the height, or the depth, whatever you want to call it, is currently 30 centimeters.